The research paper discusses the point defect kinetics equations, which describe the concentration of radiation-induced point defects in materials under irradiation. The authors employ perturbation theory to derive up to the third-order correction to these equations, enabling a full description of continuously changing rate constants. This approach can accurately predict the solution up to 50% deviation in the rate constants. The equations describe the change in defect concentration due to competing processes, including direct defect production, vacancy interstitial recombination, and defect loss to sinks. Uncertainty in the rate parameters arises from computational methods, and perturbation theory is used for parametric sensitivity analysis and uncertainty quantification. The authors conduct sensitivity analysis and uncertainty quantification on the point defect kinetics equations using perturbation analysis, investigating the effects of perturbations on 4 input parameters. The derived equations show how the change in concentration is expressed as a function of the perturbation in each parameter. This approach enables the prediction of the change in results on fine grids of perturbations, demonstrating the effectiveness in Section 3 of the paper. The authors present a sensitivity analysis and uncertainty quantification framework for point defect kinetics equations using perturbation analysis. This framework captures the response to 50% input changes and can be extended to any finite orders. The authors apply perturbation expansion to quantify the aggregated uncertainty due to all input parameters. They apply this framework to pure alpha Fe under electron irradiation, solving the equation using irradiation conditions and material parameters. The solution falls into the regime of low-temperature high-sink density scenario. The authors consider variations in KIV and KVs, introducing uncertainty based on impurities, local stress, and computation accuracy. They demonstrate results for variations of KVs and KIV at plus or minus 20% and plus or minus 50% changes, showing that a more negative alpha would lead to higher defect concentration. The sensitivity analysis and uncertainty quantification are discussed, focusing on perturbation analysis and vacancy concentrations. The results demonstrate the agreement of the third-order correction with the direct solution under various conditions, highlighting the efficacy of the perturbation methodology for uncertainty in multiple parameters. Here is the combined summary of pages 9 and 10 of the research paper. The authors conduct a sensitivity analysis and uncertainty quantification on point defect kinetics equations using perturbation analysis, as illustrated in Figure 6. The figure displays the variation of increment CV with time under different perturbation levels, beta equals plus or minus 20% and beta equals plus or minus 50%, and compares the results with the solution from solving equation 1. The dotted lines represent the results up to third-order correction based on equations 7, 8, and 9, showcasing the percentage changes in Figure 6b. Figure 7 demonstrates the variation of increment CV, percent, with time under beta equals 20%, comparing the solutions from solving equation 1 and the results up to first-order, second-order, and third-order corrections. This approach can be extended to analyze the sensitivity of other rate constants, such as K0 and KISS, in scenarios involving uncertainty in dose rate and interstitial dislocation interactions. The perturbation expansion method efficiently analyzes the response of point defect kinetics equations to uncertainty and sensitivity in input parameters. This method has the advantage of performing sensitivity analysis on continuously changing parameters by solving a few extra equations, rather than solving the original equation repeatedly. Figure 8 showcases the capability of the analyses to generate aggregated uncertainty due to uncertainty in multiple rate constants, specifically KIV and KVs, under changes of both KIV and KVs, alpha equals 20% and beta equals 20%. The solid lines represent the solution from solving equation 1 with new KIV and KVs values, while the dotted lines represent the prediction from adding the results of KIV-induced change and KIVS-induced change. The authors acknowledge the support from the Department of Nuclear Engineering at Penn State University and provide a list of references, including works on radiation materials science, modeling injected interstitial effects, perturbation methods, cluster dynamics modeling, and ab initio studies of helium in alpha Fe.